Incredibly long conversation with an AI chatbot scrolling through pages and pages of text. Or maybe you're asking it to analyze a massive document like a sprawling research paper or even a novel.
Right.
You know how sometimes it feels like it completely forgets that crucial point you made or that key detail from way back near the beginning? It's like its memory just runs out.
Yeah,
It's trying
exactly.
to keep 1,000 tabs open in your head and suddenly forgetting what's in the first 50.
That's a perfect analogy, actually. It highlights a fundamental challenge with large language models, LLMs. They were originally designed and trained with a specific, often quite limited capacity for how much text they can look at or remember at once. We call this their context length.
And how limited is that historically? I remember our sources mentioning some pretty small numbers for earlier models.
Right. The research we're looking at points out historical examples where this was often just 2,000 or maybe 4,000 tokens.
Tokens, just to be clear for everyone, what exactly is a token?
Ah, good point. Think of a token as roughly equivalent to a word or maybe even just part of a word. It's the basic unit the model processes.
Okay.
So 4,000 tokens is maybe just a few pages of text, really.
Okay, so we're talking about a very short memory span compared to the length of a large document or a complex, unfolding conversation. What happens when you feed an LLM input that goes way beyond that initial training context length?
Well, the consequences, according to the paper and notes we looked at, are pretty stark. The output is severely degraded and can become unreadable and undecipherable.
Wow.
The model effectively loses its ability to make sense of the earlier parts of the input sequence. It's not just forgetting, it's getting actively confused.
Confused. So there's a deeper technical reason than just hitting a simple memory limit.
Absolutely. The core technical issue often boils down to how these models understand the position and distance of tokens from each other in the sequence. Okay. This is handled by something called position encoding. It is essential for the attention mechanism, which is how the model weighs the importance of different tokens when generating the next one.
Right, attention.
And many current LLMs, including the ones tested in this research like Llama, use a popular method called ROPE, or rotary position embedding.
Rope. And this is where the confusion comes from in long context.
Precisely. It runs into what the researchers call out of distribution, or OOD issues.
OOD?
Yeah. The model was trained on sequences where the largest relative distance between any two tokens was capped by that original small context window.
Okay.
When you feed it something much, much longer, it encounters relative distances it simply wasn't trained to handle. It hasn't learned how to interpret the positional information correctly for tokens that are thousands or tens of thousands of positions away.
Ah.
This leads to corrupted or unpredictable representations of those distant tokens. The vectors just get messed up.
Oh, so it's like you trained it to navigate a small room, and now you've dropped it into a massive sports arena. It knows how to walk, but has no idea how far away the other side is or what relative direction even mean on that scale.
That's a great analogy. Yeah. It's trying to apply the rules of the small room to the vast arena, and the rules just don't scale correctly from those huge distances.
All right, that terrifying picture of degraded, undecipherable output makes the problem very real. So, facing this and knowing that retraining one of these massive models is incredibly expensive and time consuming, what have researchers tried? How do you fix this without a full retraining?
Well, a key direction has been developing training-free methods. One notable example mentioned in the sources is self-extend, sometimes called LongLM.
Self extend or long LM? Okay.
The core idea was quite clever. Since the OOD problem is about those massive relative distances, let's try to remap those huge distances back into a range the model is comfortable with.
Okay, remapping the distances. How did self extend attempt that?
It used a grouping strategy. For tokens that were far away from the current position, it would group consecutive tokens into fixed-size chunks.
Fixed size chunks.
Right, so instead of the model seeing token A way over here and token B way over there individually, it might just see group 1 and group 5, effectively reducing the perceived distance.
But they didn't group everything, did they? I remember reading something about a neighbor window.
Absolutely crucial detail. Yes, within a certain window right around the current position, the neighbor window tokens were not grouped. They kept their exact relative positions.
Like a group size of one.
Essentially, yes, a group size of 1. This is vital because the tokens immediately surrounding the current one are usually the most relevant, and you don't want to lose that fine-grained positional information by lumping them together.
Makes sense. So fixed, larger groups for the far away stuff, precise individual positions for the nearby stuff in the window. Where did this long LM method hit its limit, according to the research?
The primary weakness highlighted in the paper is the transition between that neighbor window and the fixed size groups. It's an abrupt jump.
Abrupt jump.
Yeah, the group size suddenly leaps from one inside the window to a much larger fixed number right outside that boundary, let's say size 8 or something.
I can almost picture the model stumbling there. What's the consequence of that sudden change?
The sources indicative of this abrupt shift can actually increase the model's perplexity. Remember, that's a measure of its confusion or surprise.
Right, lower is better.
Exactly. So perplexity goes up right at that boundary, immediately after the neighbor window.
Hmm.
And to mitigate this confusion and maintain performance, you'd often have to make the neighbor window larger.
Ah, but making the neighbor window larger?
Directly eats into your ability to extend the total context length. It's a bit of a catch-22. You fix one problem, but limit your overall goal.
Got it. A smart idea to group, but the sudden switch limited how effectively you could push the boundaries.
Exactly. And that abrupt transition is precisely what the self method aims to improve upon.
Ah, the core innovation we're here to dive into. So self builds on the grouping idea, but tries to make it smoother.
That's right. Self, standing for self-extend the context length with logistic growth function. Quite a mouthful.
It is,
It's built on a very intuitive observation about how we use language,
which is.
that the relevance of a token generally decreases the farther away it is from the token you're currently focusing on.
Makes perfect sense. The word 4 paragraphs ago is probably less important to the current sentence than the word right before it.
Precisely. And this suggests you don't need to treat the positions of tokens 5,000 words away with the same precision as tokens 5 words away. You can group the really distant ones more aggressively. Okay. So the core innovation of Self is a dynamic grouping strategy.
Dynamic grouping, meaning the group size changes, not fixed like before.
Yes, instead of a fixed group size outside the neighbor window, Self makes the size of the consecutive token groups increase the farther they are from the current query token.
Interesting. Increasing group size with distance. How do they control that increase? Is it just linear or
This is where the logistic growth function comes in. They use a function based on this specific mathematical curve to determine the group size based on distance.
logistic growth? Why that specific function? What's special about it?
The paper explains it's ideal because it's a function that increases gradually. It starts slow, speeds up, then slows down again. But crucially, it also has a defined maximum value.
Ah, a ceiling.
Exactly, a ceiling which they call capacity, or C. So it allows the group sizes to start small right after the neighbor window, reflecting that decreasing relevance intuition we talked about.
Right.
And then the group size gradually grows as you move farther out. But it cleverly puts a speed limit, or cap, C, on how big those groups can ultimately get.
So you don't end up with ridiculously huge groups that lose all meaning.
Precisely. You don't want groups to be so large that they completely destroy any useful positional information. And since group sizes have to be whole numbers, integers,
Of course.
they just use the floor of the function's output. Round it down. The paper gives the formula f high frac equals f I frac, where C is that max capacity and R controls how quickly it grows.
Okay, so the group sizes smoothly ramp up from one in the neighbor window, getting larger and larger with distance, according to this logistic curve, but never exceeding that maximum capacity C.
That's the mechanism. It provides a much smoother, more natural feeling transition than self-extends abrupt jump from 1 to, say, 8.
Yeah, I can see how that would be less jarring for the model.
And this dynamic size determines these group position indices used in the encoding. They call them GK and GQ. Think of them as calculated grouped positions for the keys and queries in the attention mechanism.
Okay.
And they specifically ensure the relative position immediately outside the neighbor window is deliberately set to the window's width, W, just to guarantee a smooth start to the dynamic grouping right after that neighbor zone.
That makes a lot of academic sense, applying a natural function to model the decrease in relevance. But okay, processing potentially hundreds of thousands or even millions of tokens and calculating these dynamic group sizes, that sounds like a massive computational task. How did they handle the engineering side to make this efficient?
That's another key part the paper focuses on, developing an efficient parallel algorithm to construct those dynamic group indices.
Parallel, okay.
Yeah, because a simple sequential approach calculating group sizes one by one down the sequence would be way too slow. It would take time proportional to the sequence length, which is just not feasible for truly long contexts.
Okay, so sequential is out. How does the parallel method speed things up?
The cleverness here is that it uses the inverse of the grouping function.
The inverse function.
Right, this inverse helps identify the exact points in the long sequence where the group size changes according to the logistic function.
Ah, so you find the breakpoints first.
Exactly. By finding these change points, the algorithm can divide the entire input sequence into sections where the group size is constant within each section.
Okay, so once you know where all the constant size sections are.
Exactly. You can then calculate and assign the correct group indices to all the tokens within one of those constant size sections simultaneously using different processing threads in parallel.
Right. Instead of step by step, you identify the structure first and then fill it in all at once, basically.
That's the idea. The theoretical work involves roughly with the sequence length plus the maximum capacity, ON plus C, and the parallel steps needed are limited by the capacity itself.
So it's designed to get much faster on hardware that can do many calculations at once, like GPUs.
That's the goal. It's built for potential near-linear speedup if you have enough parallel processors, enough threads. The runtime is bounded by something like Omax.
Okay.
Though the paper does note that in their current implementation, it's actually slightly slower than self-extend.
Oh, really? Why is that?
Because the calculations for the logistic function's inverse involve more complex math, specifically logarithms, compared to self-extend similar fixed-size operations. So a bit of a trade-off currently between the smoother logic and the raw calculation speed.
Fascinating blend of academic intuition with that logistic curve and then some clever parallel engineering to try and make it practical. All right, theory and design are one thing, but how did self actually perform when they put it to the test in
They
experiments?
ran several experiments, starting with perplexity analysis. This was done on the PG19 dataset using the Llama 2 7B chat model.
And perplexity, again, is that measure of the model's surprise or how well it predicts the next token lower is better. How did self do?
Correct. The results show that self generally achieves lower perplexity than self-extend when comparing them with the same maximum allowed group size, the same capacity C.
Lower perplexity. Why do you think that difference shows up? Is it that smoother transition paying off?
That's the key insight from the researchers. They suggest that because self moves gradually through intermediate group sizes, maybe size 2, then 3, then 4, before hitting the maximum C.
Instead of jumping straight from 1 to C like self extend.
Exactly. It provides a less jarring, smoother input structure for the model. This seems to make the model less surprised and more stable, hence the lower perplexity. They saw this difference most clearly with larger capacities and on longer sequences, where those intermediate groups have a bigger impact.
Okay, but I bet on extremely long sequences where most tokens are really far away and both methods end up using the maximum group size C anyway, the difference would shrink.
Exactly what they observe. On sequences significantly longer than the original training context, the perplexity performance of self and self-extend tends to converge
Right.
because the benefit of those intermediate group sizes becomes less pronounced when, most tokens are just grouped at the maximum size allowed anyway.
Makes sense. What about performance on actual tasks? Reading comprehension, summarization, that kind of thing, using benchmarks like LongBench and LEval. Did the lower perplexity translate?
On those real-world benchmarks, the results showed a generally positive trend. Self-demonstrated performance increases up to 12% on tasks within LEval and up to 6.4% on summarization tasks in LongBench compared to LongLM.
That's a noticeable bump in performance. Were there specific models or tasks where it's shown brightest?
Yes, it showed the most significant improvements on the Llama 27B and Qwen 7B models in LEval.
Okay, 7B models.
Right. Improving performance across tasks like reading comprehension, they mentioned quality, S-fiction, and factual recall, Coursera, TOEFL. On LongBench, using a somewhat larger capacity for self, C equals 32 versus self-extend C equals 6 or 8.
Ah, using its strength.
Yeah, self-improved performance on summarization and tasks that involve moderate average context lengths like multi-field QA and the 2-wiki multi-hop QA tasks, hotpot QA too.
And I remember reading they mentioned more predictable behavior as well, like less erratic.
They did. Specifically on the 2-wiki multi-hop QA task, they pointed out that as they increased the group size settings, like that capacity C, self-accuracy decreased more slowly and predictably.
Hmm.
Compared to self-extend's accuracy, which showed more abrupt drops sometimes, this supports the idea that the smoother grouping leads to more stable performance when you're pushing the limits of the method.
So, largely positive results showing this dynamic grouping is a genuine step forward, especially for certain models and tasks. But were there any unexpected results? Any places where self struggled?
Yes, and this is where it gets really interesting and perhaps highlights the complexity of extending context isn't a one-size-fits-all solution. They found a couple of instances of surprising underperformance.
Okay, lay 'em on me.
First, on the Llama 213B model, the slightly larger sibling of the 7B model where self did well,
Yeah,
self actually performed worse than self-extend across all the tasks tested.
worse. Not just the same, but worse.
Worse. The researchers themselves noted they found this result unclear given the architectural similarity to the 7B model where it worked great.
Wow, that's fascinatingly counterintuitive. Why would it struggle with the 13B model when the 7B worked? That points to some subtle difference that isn't immediately obvious.
Absolutely a real puzzle there. And perhaps even more significantly, they tested self on a specific reasoning-focused model, DeepSeek R1 Distill Qwen 7b.
A model tuned for reasoning tasks. Okay.
Applying self here led to a significant decrease in accuracy, a big drop.
Ouch. Why?
The researchers speculate this might be because the model's training and fine-tuning for complex reasoning, potentially involving reinforcement learning, wasn't optimized for the kind of group attention introduced by self. The way it learned to reason step by step might conflict with this grouping approach. They even observe models sometimes getting stuck in a reasoning loop.
A reasoning loop. That sounds bad. So it's not just performing worse, it's actually failing in a fundamental way on tasks where the model needs to think hard about the long text.
Precisely. While it seemed great for reading and summarizing on some models, it introduced major problems for this specific reasoning model.
Okay. Any other areas of struggle?
And finally, both self-extend and self continued to struggle on the Koji benchmark for coding tasks. Self occasionally produced nonsensical outputs there, similar to its predecessor. So coding seems to be another area where this specific approach isn't quite hitting the mark yet.
Okay, so while it's a clear improvement for things like summarization and general reading comprehension on certain models like Llama 2.7b and Qwen 7b, it is definitely not a universal fix, especially for complex reasoning or coding tasks, and mysteriously not for Llama 2.13b either.
That's a fair summary based on the data presented. It's a significant step for a specific type of long context use case and model family, but the landscape is definitely much broader and more complex.
Speaking of the broader landscape, where does self fit into the overall picture of how researchers are trying to solve the long context problem for LLMs? How should we think about it?
Right, so SL is specifically a training-free method. That's key. But it works by modifying the position encoding, fitting within the family of techniques that build upon rope. It's about tweaking how the existing model perceives distance.
And there are other fundamentally different approaches out there too, right? This isn't the only game in town.
Oh, absolutely. Briefly, the sources acknowledge other categories exist. There are attention architecture-based methods that fundamentally change how the attention mechanism itself works. Things like streaming LMM or LM infinite. They modify the core calculations.
Okay, changing the attention mechanism.
And then there are retrieval and compression-based approaches. These don't try to make the model look at everything at once, but instead intelligently pull out the most relevant parts from the long text using retrieval, or compress the context somehow before feeding it in.
Right, different strategies entirely.
Exactly. Self is distinct from these. It's specifically about altering the model's perception of the sequence structure itself via these modified position embeddings.
Okay, so it's one particular path among several being explored, focused on this position encoding aspect. Based on everything we've seen, what are the main limitations of SALF that the sources explicitly point out? Let's just recap those.
To reiterate the key limitations from the research. First, the current implementation's runtime. Although theoretically designed for efficiency, it's actually slightly slower than self-extend in practice right now because of those complex logarithm calculations in the inverse function.
Okay, performance could be better.
Second, the limited scope of testing. It was only evaluated on a small handful of LLMs and benchmarks, so we don't really know how it performs on the vast majority of other models out there.
Needs broader validation.
Definitely. Third, the major struggles with the reasoning model, leading to significant performance drops and those worrying looping issues. That's a big red flag for certain applications.
Yeah.
And finally, the continued poor performance on the code coding benchmark. Still not cracking that nut.
So some clear areas for future work and specific task mats where this method doesn't seem suitable yet, or at least needs more investigation.
That's accurate based on this research, yeah.
All right, we've taken this deep dive. We've unpacked the core problem of limited LLM contexts and those OED issues with position encoding. We looked at a previous attempt with self-extend and its abrupt transition weakness. We really explored self's elegant solution using dynamic grouping via the logistic growth function and its parallel engineering approach. We reviewed the experimental results showing its strengths, particularly in lowering perplexity and boosting performance on summarization and reading comprehension for certain models, but also highlighted some surprising limitations and failures, and we briefly positioned it in the broader research space.
It's definitely a clever and, I think, promising step forward for enabling existing models to handle longer inputs without the massive cost of full retraining, particularly excelling at tasks like summarization and reading comprehension for specific models like Llama 7b.
But those struggles with reasoning models and coding tasks, along with that unexplained underperformance on Llama 2.13b, that really leaves us with some big open questions, doesn't it?
It really does.
Could it be that the absolute optimal way to handle incredibly long context depends heavily on what the LLM is actually trying to accomplish? Is dealing with context for summarizing a novel fundamentally different at a technical level than handling context for debugging code in a huge project? Or performing complex multi-step reasoning based on a long legal brief?
It certainly seems to suggest that achieving true, robust, long context mastery across all tasks might require more than just a single general training free method like dynamic grouping. Maybe the assumptions that work for summarization just break down for reasoning.
Yeah.
Perhaps it points towards the need for task-specific fine-tuning on top of these methods, or even entire different architectural approaches altogether, depending on the end goal.
It leaves us wondering just how far these elegant training-free position encoding modifications can really take us before more tailored or fundamentally new solutions are necessary for certain critical tasks. A fascinating space with many paths still to explore.